So what we're doing here is we're saying we want the probability of obtaining a low p-value when tossing a coin where the probability of heads is 51%, right?
Mm-hmm.
So then what we want to do is we want to plot the probability of obtaining p-value of 5% or less. So the probability of the p-value being 5% or less means that if you repeat this experiment, right? So you toss the coin and tosses time, then 5%. So then this many times you obtain a p-value that's 5% or less. So you do many experiments, and then you're saying, well, what portion of those experiments did we get a low p-value?
Okay.
All right. So let's look at this function for a second. So what this function does is it runs one experiment, and then it computes the p-value for that experiment, right? So here it runs the experiment for this many tosses where the probability of heads is prob.
Right.
So here what you're saying is S1 get me like a random number. So this would be the number of heads out of this many tosses where the probability of heads each individual trial is prob. Okay. So let's try to run that. I'll just copy that. So let me set n tosses to be, let's say, 100, right? And I'll set prob to be 0.51. So in the first problem, we always have prob be 51. So what happens when I run this? S1 is a number, and it's probably going to be a number that's around 51, right? Because so on average, it's going to be 51. And every time I run this, I'll get a, so every time I run this, I'll get like a different S1. Could be the same, but like, so this time around, it worked out to be 51. So the next thing that I do is I compute the p-value that corresponds to S1, where the null hypothesis is that the probability of heads is 50%, right? So here's what I'm doing. I'm saying this is how many I expect, and S1 is how, so I expect 0.5 times n tosses if the null hypothesis that the coin is fair is true, right? So if n tosses is 100, so if this is 100, then I expect 0.5 times 100, so 50, right? And then I'm saying, well, I got this one, so in this case, I got 51, right? So 50 minus 51 is going to be minus 1. And then I take the absolute value of that, so I get 1. So in total, I get, this is 50, and then this is minus 1, so I get 49. So 49 is like as extreme as 51, but it's to the left of 50.
So it's like the lower.
Right, so it's like the lower extreme value, right? So if S1 were 49, right, what I would get is, again, just 49 back, because I would do 50 minus 49, absolute value, that's still 1, minus 1, so I get 49 back.
But the reason why we do absolute values for this reason, because we got a negative.
Right, so I always, so yeah, so this could be positive or it could be negative. So here, I always want to get like the lower extreme value. Like if I get 55, I want 45. If I get 45, I also want 145, right? So here, like the center is how much I expect. So I expect 50. And I'm saying, give me a value that's as extreme as S1, but if S1 happens to be to the right of 50, give me the extreme value that's as far away from 50, but on the other side, right? And here, 50 is because under the null hypothesis. So if the coin is fair, then I expect 50. So if the null hypothesis were different, then it would be different. So it wouldn't be like 0.5, it would be the probability in the null hypothesis. Okay. So now this function, what it does is it computes the p-value. So, and here I'm multiplying by 2. The reason I'm multiplying by 2 is I want the probability of like 45 or fewer, or 55 or more if S1 is equal to 45, or if S1 is equal to 55.
So if it, let's say if it wasn't fair, if like the null hypothesis was not, that the coin was not fair,
yeah,
we couldn't do that. So we do like this, and then 1 minus this whole p binom thing minus 1.
Exactly, exactly. Okay, so this is the function. So what the function does is it computes a p-value, and it like runs an experiment and it computes a different p-value every time, right? So I'll give it like 0.51, and here, p-val.r. So here I get like a p-value of 0.27, and then a p-value of 0.92, a p-value of 0.36, and so on, right? So I get like a different one every time. So here I got 1.07, so that's a little bit weird. The reason is that when n tosses is equal to 50, it messes things up a little bit. So because here you're saying like compute the probability of 50 or fewer, and then you multiply it by 2, but that means you're including 50 twice. So, but that's okay because we only care about when the p-value is smaller than 5%. Okay. So, all right. So now what we want to do is we want to say, okay, for different numbers, so let's first say, okay, so let's say that n tosses is, 100, right? And then maybe we want to know how often for n tosses equals 100, how often would the p-value be smaller than 5%, right? So to do that, we just replicate this, let's say 1,000 times, right? And we'll say n tosses here, and we'll give it 0.51. Right? So those would be like all the p-values. And then to know how, so let's try to run this. So we got like all of those p-values. If we want to know how often that's smaller than 5%, we can just say smaller than 0.05 and then do the mean of that, right? So that would be like a mean of a vector of ones and zeros, right? And this would be like the proportion of the time that this is zeros or falses. So if we compute that, what we see is that the p-value was smaller than 0.05, like about 5% of the time, actually a little bit less. Okay. So we could try to increase the number of tosses. So let's make it like 10,000. So if we increase the number of tosses to 10,000, what you see is that 50% of the time, slightly more, we reject the null hypothesis. The p-value is smaller than 0.05. If we make it like 100,000, then you'll reject the null hypothesis every time. Okay, so we can look at the actual p-values. And well, this is smaller than 0.05, but here we can look at the actual p-values and you see that they're tiny. So intuitively, it's pretty clear what's happening, right? So if you have a probability of 0.51 of getting heads, like if you toss the coin 100 times and you get 51, that's what you'd expect, right? That's like the thing that would happen the most often. Well, you couldn't distinguish that situation from a situation where the coin is fair, because if the coin is fair, you'd get like 51 all the time. On the other hand, if you toss the coin 100,000 times, then you'd get like 100,000 on average. You'd expect like times 0.51, right?
It's a bigger difference.
So you'd expect, so you'd expect 510,000 on average. So you'd be like 10,000 away from what you'd expect under the null hypothesis. So obviously you'd reject the null hypothesis every time because that's really different. Okay. So now what we were trying to do is we were trying to like make a graph like for different numbers of n tosses. So that means that we want to make a function that takes in n tosses and then runs this experiment, right? So let's do that. So we'll call it like prob reject or something. And that's going to be a function that just takes in and tosses. And so, I mean, here I did like 0.51. I could make a function that's kind of more flexible and say I want to also give it the probability. And here I'll plug in the probability as well. And we'll just return this quantity, right? So we'll return the probability of rejecting. In other words, the probability of getting a p-value that's smaller than 5%. Right? So now we don't need this. So we say prob reject. So let's try it again. So I'll say n tosses is, let's say, 1000, and prob is, let's say, 0.51. I'll get 10%. If prob is like 61, I'll get 1. Why? Because kind of this is different enough from the hypothesis that 1000 tosses is enough. So if I do like 0.55, well, that's what I get. So okay, get 0.53, it's going to be lower. So okay, all right. So now what we want to do is we want to just run this function for different numbers of tosses, right? So I can say like all n tosses, and let me start with like 10, go to 100, 1000, 50,000, 100,000. Well, that's a bit of a jump, so let me also add like 20,000 and 50,000, 100,000. Let's do like 75,000 as well. Okay, just so that we're not spending a lot of time running this. So you could also do something like sequence, yeah, so like 10, 100,000, like 5,000, whatever. So that would also work, right? In fact, let's do that instead. So all in tosses is going to be this. And now say sapply all in tosses. And then I'll say that the function is prob reject. And then I also need to supply the prob, so that's going to be 0.51. So every one of the all n tosses is going to be sent to n tosses here, and then 0.51 gets sent to prob, right? And this is, we'll call it like all prob reject, like this. So if we run it, so we got the probabilities, so now we just put them in a data frame and we can plot them, right? So we can say, so let's say prob reject df is data.frame. And now so here I'll just call the column n tosses, and that's going to be equal to all n tosses. And I'll call this this one prob reject, and this is going to be all prob reject, like this. So let me run this. Let me see what it looks like. So here I get like n tosses, and here I get like probability of rejection, right? So now let me do library tidy first, just to get everything out of the way. And now I'll say like ggplot, so prob reg df. And here I'll say plus geom_line, let's say. And I'll do mapping as AS. So here the x-axis would be the n tosses, and the y-axis is going to be prob reject. And let's run that. And you get this kind of curve, right? So basically you start out with a 0 probability of rejecting, and as you go up, you get a probability of rejecting that's basically 1.
So can you say that, like from values, like over here with 0, that's like a type 2 error?
Yes. So so basically, because the null hypothesis is false, so 1 minus this probability would be the type 2 error for this situation. Right? Cool.